Let's now have a look how we can evade the impossibility proofs for two-party crypto. Here we will have a look at a fun example exploiting option 3. Namely, we will assume that Alice does not hold the purification of the protocol. If you wish, assume that Alice and Bob share their state, row AB. But now, instead of the malicious adversary, for example Alice, also holding the purification, we will assume that this purification is somewhere outside both of their labs. And the easiest way to think about this is to imagine that there's a third party, which I will call the wizard, which holds the purification W. Note that Alice and Bob's states could thereby even be classical. In other words, Alice and Bob could also have a classical state, row AB. Meaning that Alice has a string S, Bob has a string T, and they're giving these random strings this randomness with some probability P as T. Such models are indeed known in classical cryptography for a long time. For example, if Alice and Bob were connected by a channel with some guaranteed amount of noise, as considered by Claude Crépeau, then this could be modeled by such a wizard. Concretely, it could also be that the wizard is what is called a trusted initializer in the works of Rivest. Before the protocol starts, the wizard will provide Alice and Bob with some very special shared randomness. This means that he's the one who's going to choose these classical bit strings, S and T. He sends S to Alice and T to Bob over private channels, so only Alice learns S and only Bob learns T. Rivest proposed a commitment protocol that we will now have a look at. Before delving into commitments and the protocol, let's first agree on what kind of shared randomness the wizard will actually give to Alice and Bob. I will describe this here as if they could communicate infinitely many bits, in the fully continuous case, but of course you can imagine that we suitably discretized to some finite precision. So what is the wizard going to do? First, the wizard will pick a random line. For example, this one. And this line is characterized by two numbers, A and B. So you can think that the wizard really picks two numbers, A and B. A is the slope of the line, and B is the offset. In other words, the point where the line intersects the y-axis. The string S that he sends to Alice is thus S equal to A and B, the slope and the offset. The wizard then picks a random point on the line. And he does that by picking a random point on the x-axis. Say this one. And we'll call that x. He then evaluates y being equal to a times x plus b, the corresponding point y. And he sends to Bob t, namely the random point on the line. Why does this correspond to Alice and Bob having a mixed state? Note that we've seen how to write classical distribution as mixed states. And of course, if they have a mixed state at the beginning of the protocol, given by some shared randomness S and T, also the state at the end of the protocol will be mixed. Note that the purification always remains with the wizard of the entire subsequent protocol. So Alice gets A and B, Bob gets X and Y, according to some uniform distribution over lines and the point on the line. Applying the rule how to write density matrices, we thus see that we can express the states that Alice and Bob share as follows. And it looks exactly the way that I've written it before. Where this here was S, and this here was T, and I'm not rewriting Y here because Y is already defined as AX plus B. This is clearly a mixed state. If you want, we can construct its purification. This can easily be achieved by giving A and B and X, if you want also Y, to the wizard. So if Alice has A, and B, Bob has X and Y, then the wizard also has A and B and X and Y. You should convince yourself that if I now trace out the wizard's registered W, I'm back to that state over here. I'm now claiming that we can use this very funny randomness to do a commitment. This time, we will, however, not be committing to bits, but to real numbers R. Or if you want, imagine again that we will discretize this appropriately, but I'll just work with real numbers here. So in the commit phase, Alice puts the number R that she wants to commit to in the envelope. And in the open phase, Bob recovers R. Let's briefly remember that we want two things. First, the protocol should always be correct, meaning that if Alice committed herself to the number R, Bob should also accept R when she opens. Second, we want the protocol to be secure. Alice cannot change her mind about R after the commit phase. And Bob cannot learn R before the open phase. So how can we now make a protocol for this task? In other words, how can we use these points and lines to commit anything? The idea is quite simple. And let me write above here what Alice and Bob have. What is the shared randomness that they're given? At the start, Alice has her line and Bob has his point. Now to commit to a number R, our protocol is going to go as follows. Namely, to commit, Alice is going to take her number R, say this one, and she's going to evaluate the line at the point R. So she gets, let me call it YR, so YR is F applied to the number R, A times R plus B. And to commit, Alice will send to Bob F of R. She sends Bob this coordinate, Y of R. Now, Bob has this coordinate. Before we actually continue, let's convince ourselves already whether the protocol is secure against Bob. Because remember that after the commit phase is over, in this case after Alice sends to Bob YR, Bob should not be able to figure out what is actually R. Note that this is clearly the case. He has only this one point, but there's infinitely many lines that could run through this point. And each of them would result in a different R. Hence, Bob cannot learn R, except in the, of course, very unlikely event that it's the same as his point up to arbitrary precision. To open the commitment, Alice now tells Bob two things. So to open, she will send him R, what she wants to reveal, and she actually now tells him what the line is. Namely, she sends him A and B. Now Bob does some checks. Namely, first he checks, is my point, the one that I obtained before, actually on the line? And if not, he aborts and accuses Alice of cheating. So if no, then he rejects, and if yes, we continue. He also now checks whether the open point is also on the line. So he has already YR from the commitment, and now he also has R, and he checks, is that point also on the line? If yes, he accepts R, but if no, then he rejects and accuses Alice of cheating. Remember, we still have to check whether the protocol is correct and whether the protocol is secure against cheating Alice. Let's first check correctness. If Alice and Bob are honest, so Bob is not trying to do anything like this, then Bob surely accepts. All his checks succeed. He's going to identify this point, and both the open point as well as the previous point lie on the line. How about security against Alice? If Alice is trying to cheat, remember that we want to make sure that she cannot change her mind. So what could Alice possibly do here? If she wants to cheat, meaning that she wants to open a different point or head, then she needs to send to Bob a different line. Namely one where she has the same Y value, but a different R. This R, this R head. Unfortunately for Alice, she has no idea what the point is that Bob actually has. But Bob is going to check whether this point is on the line. So to come up with a new line that gives Alice the desired fake R head, and at the same time matches Bob's point, is not possible. If we discretize the protocol, there might be a small probability, but it's extremely unlikely. So the probability that she can cheat is negligible. While I have not given any formal proofs here, you can thus see that Alice and Bob can perform commitments even using classical communication if they're given very special forms of classical shared randomness. Of course, in practice, randomness does not magically fall from the sky. So let's have a look at another assumption that does not need such randomness.